Hello, welcome to SPMM Revision on Demand. In this podcast, I will discuss the concept of confidence intervals in statistics. When we conduct a study, we examine a sample which we think is representative of the population from which the sample is taken. The result from our sample can only be an approximation of the true value in the population. In this example, you can see that the sample mean is somewhat removed from the population mean. We need some numerical measure that can tell us how good our approximation is to the real population value. To see how close a sample's result is to the population's true result, researchers often make use of confidence intervals. Confidence intervals are based on the results estimated from a sample, but they provide the range in which the true population value is likely to lie. Consider the example of average height of boys in a classroom. Let us take a sample of 6 students from a batch of 42 students in this population. If we say the mean height of boys in our sample was 170 centimeter and the 95% confidence interval was 160 to 180 centimeter, by this we can conclude with 95% confidence that the average height of the population lies between 160 centimeter and 180 centimeter. In other words, if you look at the mean height of boys in 100 independent samples taken one after another from a population, 95 out of 100 times the mean value would fall between 160 and 180 centimeter. How to make sense of confidence interval values? The narrower the confidence interval, the more precise an estimate is. That is, if the 95% confidence interval is 165 to 175 centimeter instead of 160 to 180 centimeter, our estimate can be said to be more precise. Higher precision also suggests better representativeness of the sample to the population. Precision can be gained by increasing the sample size. The larger the sample, the more representative it will be of the population. Confidence interval can be calculated for group means, estimates of effect sizes, relative risks, odds ratios, NNT, etc. Let us consider an example. In the general population, mean age of fathers when their children are born is 28 years. There is some suggestion that older fathers have higher risk of having children with psychosis. Suppose we are interested in determining the mean paternal age in patients with schizophrenia. 50 patients are recruited for this purpose and their records are checked to assess paternal age at the time of birth. We find that the mean paternal age of the sample is 29.5 years. We also obtain a 95% confidence interval, which is 25.1 to 32.5 years. Now, this 95% represents the degree of confidence. This derives from the complement of conventional p-value or probability of type 1 error, which is alpha, which is usually 5%. So 100 minus 5%, 100% minus 5% will give you 95%. So if you wish so, you may assess the intervals for 90% and 99% confidence interval as well, but in usual practice, it is the 95% degree of confidence that most researchers report. In this case, we are 95% certain that the true mean paternal age for patients with schizophrenia lies between 25.1 and 32.5 years. These are the lower and upper limits of our confidence. The width or the range is the difference between the upper and lower limits. A wide interval of confidence indicates that the estimate is imprecise. A narrow one indicates a precise estimate. As these limits include the general population value of 28, we can conclude that there is no evidence from the study that the paternal age at birth for schizophrenia patients is higher than that of general population. So to recap, when we obtain a point estimate of any measure from a sample, it is preferable to support our estimate with a degree of confidence. And usually 95% degree of confidence is what researchers report. If there are 100 different samples drawn from the same population, what will be the point estimate of each sample 95% of the times? In other words, what is the range in which 19 out of 20 observations would fall? The answer to this question is given by the confidence intervals. So we can find this range without resorting to undertake 100 samples. In the previous example, we saw a mean of 29.5 years and 95% confidence interval of 25.1 to 32.5. At this point, it's important to remember that the limits of 95% confidence intervals does not mean that the 95% of patients in a sample will have values in this range. It only means that if the same study was done 100 times, 95 times the results will be within the range reported here. So in practice, we can calculate confidence interval for a range of summary measures including RR, OR, ARR, NNT, etc. When computing confidence interval for group comparisons, we need to see if the upper and lower limits pass through or embrace the values of no difference. This will help us to infer the statistical significance of the results. We will see this in more detail in the next few slides. This table shows the values of no difference for various measures used in reporting the results of a study. As you can see, odds ratios and relative risk, the value of no difference is 1. So for all ratios, the value of no difference is 1. But for subtractions or differences in mean values, it is 0. For NNT, it is infinity, as NNT is nothing but an inverse of a difference measure. In a group of patients with a history of hip fracture compared to healthy controls, the odds ratio for several variables considered to be risk factors for hip fracture are listed here. From the limits of the confidence intervals, we can see that all of these are statistically significant except for ex-smoker status. The values highlighted in yellow here have both upper and lower limit of confidence greater than 1. They do not embrace or cross 1. These are significant and suggest an increase in risk as they are both greater than 1. For hormone replacement therapy, these values are both less than 1. They do not embrace or pass through 1. These are significant but suggest a reduction in risk as they are both less than 1. For ex-smoker status, the confidence limits vary from 0.91 to 1.16. This includes the value of 1, so this is not a significant result. Look at this forest plot. This is a forest plot reporting relative risk ratio. The values highlighted within the red box. Both of these are less than 1. They do not embrace or pass through 1. So the pooled result is significant and suggests a reduction in relapse risk with lithium. There are 3 results that are non-significant. Can you find them? As you can see from the forest plot, these 3 boxes highlighted in yellow, the values within these boxes embrace or cross the line of no effect. The confidence limits also cross 1. In this forest plot, standardized mean difference is reported. For SMD, 0 is the value of no difference. In the red box here, one value is less than 0, the other is greater than 0. So these limits pass through 0. The pooled result is not significant. There are 2 results that are significant. Can you find them? As you can see from the forest plot, these two results do not cross the line of no effect. The confidence limits also do not cross 0. So these are significant. Confidence intervals inform us about the degree of confidence on the representativeness of our sample, precision of the observed results, clinical significance, which is inferred from looking at the magnitude of the effect, and finally, the statistical significance. I hope you can now see the usefulness of confidence intervals. So it's time to ask yourself a few questions. Thank you for choosing SPMM course for your revision.